share my screen here. Okay, everyone, good morning. Let's get started. Let me share my screen here. Okay, so before we move forward, starting the chapter number 4. So do you have any questions before we start? Questions about the previous lectures? All right. All right, so today we're going to talk about the multi-point analysis of a Mendelian loci. All right, so here we try to use statistical method to analyze multiple loci along a chromosome. So these loci are linked, and we're gonna use the statistical models or method to analyze. All right. So let's introduce the Markov chain. So Markov chain is actually model, a chain model, which is commonly used in statistics. And in the future, you're going to see this method very often in your own study. So if you study the genome and if you want to study the multiple loci, this is a commonly used way to do this. So Markov chain is actually a random process that undergoes the transition from one state to another on a state base. So for example, just look at the diagram on the right-hand side. So I'm close to the. It's kind of like noisy outside. All right. So this is a very simple example for the Markov chain. So in this Markov chain model, we only have like two status, E status or E state or A state. So we only have like two states, and the transition is between these two states. So for example, if the current state is E, let's say the T equals to 0. Suppose T equals to 0. And at this time, so the current state is E. So if we want to see what would be the next state at T equals to 1, so there are two possibilities. Either for the next time point, the chain will remain in the E state. So for example, the next state will be E state as well. So the probability to stay within the E state will be 0.3. So this is one possibility, one possible outcome for T equals to 1, or at T equals to 1, it could be the chain could migrate into the A state. So this is another outcome for the T equals to 1. So what's the probability? So the probability, the transition probability from state E to state A is equal to 0.7. As you can see, so there are only two possible outcomes, right? For t equals to 1. And the probabilities for these two outcomes add up to 1. All right. So now suppose the realized state for the t equals to 1 is A. So now the current state is A. State is A. For the next time point, let's say when t equals to 2. So what would be the outcome state for this time point? So also there are two possible outcomes. If the current state is A, there are two possible outcomes. One is like for the next time point, t equals to 2, the chain will still stay in the state A, so with the probability of 0.6. Or it can be a transition to the E state with the probability equals to 0.4, and these two probabilities will add up to 1. So this is how the chain goes, right? And as you can see, for a specific time point, the state for this time point only depend on the state in the previous state, in the previous step, in the previous time point. All right. So then that's a very important property for Markov chain is the memory listless. So it cannot. So it has a very short memory. So the current state for the chain only depends on the state of the previous step, the previous time point. Anything occurs before that will be totally like forgotten. So so this is the important feature for this Markov chain model. All right. So we're going to use this Markov chain model to help us analyze multi-loci that are linked in the same chromosome. All right. So for example, in the future, you can see in some situations, the Markov chain can be used to analyze the DNA sequence. So this is a DNA sequence, right? And we know like for each locus, there are 4 possible states rather than 2, right? So these 4 states represent 2 different letters, bases. And so suppose the current locus, the letter is G, and when we want to see what will be the next letter in the next locus, so there are 4 possible ways, right? Either for the next locus, the state will stay within the G state, or it can be transferred to any of the 3 other states with different probabilities. So for a Markov chain, usually you're going to see a diagram like this. You're going to see the different states, for example, 4 states here, right? And you're going to see the arrows coming from or to each of these 4 states with different probabilities. And these probabilities are called the transition probability. And it shows the possible transition between states. Yeah, how likely this transition will occur. All right. All right, back to our business. So we're gonna use this Markov chain to help us study the multi-loci which are linked. So for example, this is what we have learned before, right? So we have a chromosome, and we know 3 genes are linked on this chromosome. And suppose the 3 genes are arranged like this. All right, and let's start from a simple design, backcross design. So let me remind you. So what is the backcross design? Backcross design is like when we have a F1, for example, heterozygous. If we cross back to one of the pure parents, let's say A1, then that is the backcross design, right? And for the progeny, there are only two possible genotypes, either A1, or A1, A2. What's the probability for this two progeny? One over two, right? So for each type of, there are two possible genotypes. If we just look at the A locus, so for the backcross design, we only have like two possible genotypes, right? With the equal chance, 1 over 2. So that's the backcross. And this is true for all three loci here. So for A, so if this is a backcross design, we have two possible outcomes, right? Two possible genotypes. This is the same for B and C. And all right, since there are two genotypes, we can use two states. Here we say two states, right? To describe this Markov chain property here, right? So we have two states, and for each locus, the genotype will transit between these two states. So either state one and state two. Okay. And we're gonna start from locus A to see how the Markov chain can be used to describe this multi-loci. And as I mentioned, so if we start from the locus A, so when we want to study the probability of any genotype at locus B, so this the state for B, the genotype for B only depend on the previous step, which means only depend on the genotype of locus A. All right, let's look into this. So before we use the advanced statistical theorem to analyze the multi-loci. So let's introduce the conditional probability first. All right. So let me use this slide first. So in statistics, in probability theorem, all right. So hopefully you still remember, we use probability equals to 1 to describe the entire sample space. So look at this diagram. So the rectangle represented the entire sample space, and the entire sample space means the all possible other outcomes for this experiment. All right, and so of course the probability for the entire sample space will be equal to 1. And within this sample space, so we have some like events of interest. For example, the events A is described by using this circle. And another events B will be denoted by this circle. And of course, in some situations, so you're going to see there's an overlap between events A and events B, right? So, okay, so when we talk about the probability, there are two types of probability. One is the observed absolute probability, or in short, we just say probability. That's a simple probability. So if we want to see what is the probability of events A, so it's very easy, right? We just calculate the area of A, area of the circle A divided by the area of the total, right? Of the total, the rectangle. So that's the probability. That's the absolute probability, or just probability of events A. The same for B. Right? But sometimes, yeah, if we are interested in something like this, if we are interested in something like this, we want to calculate the probability A given B also occur. Then the probability is a little bit complicated, and we call this probability as a conditional probability. And in statistics, so we just define the conditional probability like this: the probability of event A given B. And mathematically, this probability equals to the ratio of this. The numerator is actually the joint probability of A and B, which is defined by the shaded area and divided by the total area of events B. So that makes sense, right? Because we want to see the probability of A given B. So which means we only consider the area within the B, circle B, right? That's the redefined sample space. That's the sub-sample space. We need to consider in this situation. And within the area of the B, we want to see what's the proportion that A also occurs, right? So intuitively, this is very easy to understand. So, so in many cases, we use this formula to calculate the conditional probability. And sometimes, like if the joint probability is not that easy to figure out, so we can use this formula to help us to calculate the joint probability, which is the product of the conditional probability given the absolute probability of an event, so something like this. Okay. So this is an example. Just show you how we understand the conditional probability. So suppose this is the entire sample space. So we have like 5 marbles in this bag, and 2 of them are blue and 3 of them are red. So if you just randomly choose one, so it's easy to figure out like the probability to have a blue marble will be 2 out of 5, right? And the probability of the red equals to this. So that's the absolute probability, the simple probability. However, if the question is described like this, so all right, if you so you if you got a red marble before, then the chance of getting a blue marble is what? So this is not a simple probability problem now. It's a conditional. So given you already got a red out of the bag, so now as you can see, you got a newly defined the sample space, right? This sample space is not the original sample space. It's a sub-sample space. Then you need to reevaluate your probability. So given this situation, given you already got a red one, so what is the probability that for the next one you can get a blue? So in this case, it's 1/2, right? So, however, if for the first draw you already got a blue one, then you're gonna see the subsample space is totally different from this one. And in this case, you have to re-evaluate your conditional probability. So now the probability of getting a blue, given you already got a blue from the first draw, this probability becomes 1/4. And this is the formula we can use to do the calculation. So this is just a very, very brief review about the conditional probability. I hope I can help you. I can remind you of what you have learned in your statistics class. We're going to use these formulas to help us analyze multi-loci in our business. Okay. Okay. So this is what we are familiar with, right? So we have 3 loci A, B, C, and they are linked. And so this is a back-cross design, so a simple design. And so we start from A. Okay, so when we start from A, because we knew for this A locus, we have 2 possible genotypes, right? All right, so this is a cross like this. Cross A2 and A2. Right, okay. Now we have like equal chance to have 2 possible genotypes from this backcross. That is why we say probability of A equals to 1. If we said this is 1, genotype 1, state 1, and this is the genotype 2, state 2. Okay, now we can easily understand the probability of A locus equals to state 1 or genotype 1, which is this, equals to the probability that A locus takes the second state or the second genotype, right? They are equal to 1/2, the equal chance, because this is a backcross design. Any questions here? Okay, very good. All right. Okay, now the time t, the t equals to 0 is easy, right? We start from the one end of the Markov chain. That's easy. But the complicated thing is like if we want to move the locus from locus, we want to move from locus A to locus B, then this is a one transition in the chain, right? If you just treat the chromosome as a chain, Markov chain. All right. So okay, now, so here we use this table, this matrix to represent the transition probability. I hope you still remember. So when I first introduced the Markov chain to you, so I have mentioned like usually we're going to use this kind of like diagram to show the probabilities of transitions between states, right? This is the same. So actually we use a different form to represent this transition matrix. This is transition probability. We use this. Okay, so this transition matrix means like here we want to see the transition probability between A and B, two loci, right? And if at locus A, the state is 1, and when we look at the locus B, the genotype or state is also 1. So which means like in this step, the Markov chain didn't change the state, stay in the same state, right? So which means like for locus A, we see the genotype is this. And for the locus B, we also see the same genotype. So this is 1, this is 1. So even there's a 1 step, but the chain stay in the same state. All right. What is the probability for this? So if locus A is the state 1 and locus B is also state 1, means there's no crossover between A and B. Do you agree? All right, the probability for this transition should be 1 minus R AB. Do you agree? Yeah, because RAB is the probability of having a crossover between A and B. So 1 minus RAB is the probability without the crossover between A and B, right? So I hope this is clear. So this is a probability, and this is the same. So if you see here, so we use this to represent this probability, right? All right. Now we see if from A to B, if the state remains in the first state, then the probability is like this. How about this? If at the beginning, the A locus takes the second state, second genotype, and when we look at the B locus, yeah, the B also takes the second state, the second genotype, then there's no crossover, right? So you're going to see the same probability at this element in the matrix, 2 by 2 matrix. Does that make sense? This is the transition matrix. Any questions here? All right. So now it should be very straightforward to understand this, right? These two elements in this transition matrix means, let's look at this. Suppose A takes the second state at the beginning, the second genotype, and when you move to the locus B, you see a different state, the first state, the first genotype, which means there's a crossover occurring between A and B, right? And what's the probability? This is the probability, right? Yeah, the same for this one. Is that clear? All right. So I hope you understand that. So this matrix is actually equivalent to the diagram I just showed you in the example of a classical Markov chain, right? This shows the probability of transitions between different states in this Markov chain model. All right, so now we can it's easy for us to write this transition matrix for the transition between locus A and locus B. And each element actually represents the specific probability for that transition, right? And it is the same. So if in the final exam, if I ask you to write the transition matrix for the B and the C. So what is the transition matrix between locus B and C? So it should be easy for you to write that, right? So the same format, but you have to replace this RAB by RBC, right? Does that make sense? Okay, good. All right, so once you have all this transition matrix specified, then we can use the conditional probability theorem to calculate the joint probability. So what's the probability for a specifically observed genotype in a progeny? So we can use this formula to calculate this. All right, let me give you an example here. So suppose from a backcross design, remember we're still dealing with this simple experimental design, right? And for each locus, we have two possible genotypes, 1 or 2. And so if you get a sample, if you get a single progeny from your backcross experiment, and if you see the genotype for this progeny is like this. For the A locus, you see the first genotype. For the B locus, you see the second, and the C, you see the second. So what's the chance for you to have a genotype like this from this backcross design? So this is how we do the calculation, right? Okay, so we put a 1/2 here. What is the 1/2? Can anyone tell me? Yeah. That's the starting point, right? Because at the locus A, so no matter what genotype you have, the probability is 1/2. So the probability to have the genotype 1 for the locus A is 1/2. So that's why we put a 1/2 here. And okay, given the first locus A, then what is the probability for us to see a genotype 2 for the B locus? So within this transition matrix, we need to find that A equals to 1, but B equals to 2. It should be this one, right? We need to look at this one. So what's the probability for this one? So that's the RAB, means there's a crossover between A and B. Yeah, of course, if you see A equals to 1, but B equals to 2 genotype, then there must be a crossover occurring between them, right? Then this must take the value of this. Does that make sense? Yeah, okay. Now, okay, once we're done with this, we just totally forget about this because the Markov chain is a memoryless list, right? So when we consider the locus C, we only need to check the states for the locus B. Okay, so this is the Markov chain. Okay, now given B equals to 2, and if you see C also takes the genotype of 2, which means there's no crossover between B and C, right? All right, and if you just think about this, this is the transition matrix between B and C, then from this matrix, we need to look at which one, this element, right? This is the element means the probability of C being equal to 2, given B also equals to 2. So that's something like this, but you need to replace this RAB by RBC. Okay, and so I'm going to talk about more complicated situation, but this is the most important one. Easy, everybody need to understand, and I could give you some questions like this. I can give you some values about the RAB and RBC, and I will ask you to help me calculate the probability of a specific genotype obtained from this backcross design. And you need to use this formula and find the right numbers to calculate this probability. Any questions here? Okay, so that's the one way that we can use to do the calculation. It's easy, but usually when we use computer to help us analyze a huge amount of data, so we would like to use matrix to help us do the calculation. So this slide shows the matrix presentation, the same situation, but we use a matrix to help us do the calculation. All right. Since this is a backcross design, okay, we only have like 2 possible states, right? 2 possible states, genotypes for each loci. And so then for each loci, A or B or C, we can use a 2x2 matrix to represent different genotypes. So for example, so if this is for the locus A, we use this matrix to represent the first genotype, which means like A equals to 1, the first state. So this 1 will take this element, diagonal element here. And if the locus A takes the second state, second genotype, then we put the 1 here, the lower end of the diagonal element for this 2x2 matrix. Okay, now if we want to calculate the probability of this genotype, so this becomes like this. So when you do the when you do the coding using R language, so you can easily, I'm gonna don't worry, I'm gonna give you some examples in the practice. I'm gonna write some code for you to translate that calculation into this matrix using this matrix format, and you can figure it out, easily figure out so what is going on here, and then so this is a more efficient way for us to solve the problem like this. So suppose the same question, right? If this is the observed genotype for a progeny from the backcross design, so what's the probability of getting this progeny? So 1/2, the same, right? And this is the genotype for the A, and this is the genotype for B locus and the C locus. And this is the transition matrix we are very familiar with. The two, this is from A to B, right? And this is from B to C, the same. And to facilitate this matrix calculation, we have to use some like identity matrix here. So here, the J is called the unity or identity, a vector or matrix. Sometimes it's a matrix, sometimes it's a vector. So this doesn't change anything, but this just can coordinate with the dimensionality when we deal with different matrix calculation using a matrix of different dimensions. So, and after you simplify this, you're gonna get the same results. This is the same results we got in the previous slides, right? As we got from the previous slides. The same here. All right. Which means like to fully understand this part, probably you have to spend a little bit of time to refresh your memory about the matrix calculation. So I don't want to spend too much time in class to talk about this, but yeah, please after class, just if you have some textbook, so you can just quickly review that part, or you can easily like find some stuff like by Google, just find some stuff and review the matrix calculation by yourself to make sure you understand how this matrix are being used in this calculation. All right. Okay. Any questions so far? All right. Okay, so all right, we are done with the most simple situation, which is the backcross. Now let's talk about a little bit more complicated situation, the F2 design. As we mentioned before, right? F2 design is is more complicated than the backcross. However, if you pay more efforts, you got more, right? You got more from your experiment, which means like you can have better resolution of the data, which can help you get more confident test results. All right. All right. So for F2 design, for each of the three loci, we will have 4 possible genotypes, right? So if you think about like cross between A1, A2 with another A1, A2, then those are the 4 possible genotypes resulting from this cross, right? F2 cross. Okay, then of course, now you have like, suppose, because if you look at these 2 genotypes, they are identical, right? If you do not know which allele is from which parent, then these 2 genotypes, you cannot distinguish these two genotypes, right? But suppose we can successfully distinguish these 2 from each other, then we have like how many states? We have 3 states, right? 4 states. We have for each locus A, B, or C, we have 4 states representing 4 different possible genotypes from this cross, F2 cross. And okay, now then for the transition matrix, if we want to find out the transition matrix between A and B, then instead of having a 2x2 matrix, which is for the backcross, right? For this F2 design, we will have like 4x4 transition matrix. All right. And for each element actually represented the probability of the transition between these 4 states. Does that make sense? Any questions here? So what is the probability for this one? What is this probability what does this probability refer to? Can anyone tell me?
2 parental type.
Yes, very good. Yeah, there's no crossover, right? From here to here. Yes, very good. All right. So this is the state 1 to state 1, right? Okay, and this is the probability from state 1 to state 2, right? Which is B1, B2. Okay. Very good. So this is a little bit more complicated, and so if you think about this, think of this 4x4 matrix as a square of a 2x2 matrix, then they are the same, right? Actually, because actually so if you look at the difference, if you compare difference between compare the backcross with the F2, yeah, you're gonna see for backcross you use this simple 2x2 transition matrix, but if this is a F2 design, it's a so this complexity will be doubled, squared actually. So if you square this 2x2 matrix, you're gonna end up with this 4x4 matrix. So that's the relationship between this the basic backcross design and the more complicated F2 design. All right, so this is important. So in the exam, probably I can ask you to help me construct this 4x4 transition matrix for me. So you need to know how to find these probabilities correctly. Okay. Okay. All right. Now, if you feel comfortable with the example I showed you here, so if you are comfortable with the example here, then it should be no problem for you to solve the problem here when we have a F2 design. So suppose you can construct this transition matrix between A and B for this F2 design. And if I told you like, okay, you need to use this to calculate the probability for a specific progeny. So suppose we observed a progeny which takes the genotypes like this. So for the A locus, it's the state 1. For B, is state 2, and for C is state 3. So what's the probability for us to have a progeny like this from this F2 design? Right? So this is the same, right? We just need to, okay, can anyone tell me why this is the case? 1/4 rather than 1/2. Because we have 1, 2, 3, 4 states, right? For the first locus A, and for each one, the probability is 1/4. So since the first one, locus A takes the value of 1, so we will multiply this 1/4 at the beginning, right? That's the probability of seeing A equals to 1. Okay. All right, and then once we have the A equals to 1, so what's the probability we have a B takes the state of 2? All right. Then from this transition matrix, we need to look at the element like here, 1, 2, right? This is the place we need to look, right? Look at, all right. That's the probability of seeing B equals to 2 given A equals to 1. Okay, now the next step. So given B equals to 2, what's the probability for us to see a C equals to 3, right? It's the same. Just think about this is we use the same transition matrix for TBC as well. So since this is like from 2 to 3, so we need to look at this one here. And you're gonna immediately see why we have a value like this here, right? But you have to replace this RAB square by this RBC square. Okay. Any questions? All right. Okay. All right. So this is, as I mentioned, this is the ideal situation for the F2. And in this ideal situation, we assume that we can successfully distinguish this genotype from this genotype, right? But in practice, this is not always true. All right. So in practice, sometimes, like for most of the situation, since we cannot distinguish genotype number 2 and number 3, so we have to put these two states together. So we have to combine these two states together. So which means we instead of having like 4 states, we only have like 3 states, but we still use the same notation here, because since we cannot distinguish genotype number 2 and number 3, so this ambiguous situation can be denoted by this. So suppose for this genotype, for the locus A, it's very clear. This is the first state, right? But for this genotype, at the locus B. So we don't know if this one is from the second state or the third state. Then we just use this to combine these two possible states. Yeah, the 2 and the 3. It could be like 2 or 3. The same for the locus C, right? Because C is the heterozygous. We don't know for this locus, this genotype is from the second state or the third state. So we just use this to represent the genotype for locus C. Since this genotype could take two possible states, then we have to add all these two probabilities together. So that's why in this formula, you're going to see we add 2 and 3 together to calculate the sum of the probability of seeing this genotype. Does that make sense? Okay. All right. So don't worry. So because this is a little bit complicated, I just show you here to make you to help you better understand the situation. But in the final exam, I let me see. I probably oh no. So sorry for this one. This is still within our radar range. So. In the final, I could ask you to calculate this for me, but for later, I will show you more complicated situations. So don't worry about that. I will not put those questions on the final exam. But for this one, yeah, I could put this one on the final exam. I could ask you to calculate the probability of this genotype if we cannot distinguish the genotype number 2 and number 3. So you have to add up the probability of these two possible states together to get the right answer. Yeah. So for example, if we want to calculate the probability of this, so let me show you the previous slides. In the previous slides, the same thing here. It's the same. Yeah, similar things. So if we can distinguish the genotype of number 2 and number 3, so this is easy, right? We just find this solution immediately. However, if we cannot distinguish these two genotypes, so we have to add these two together. So what does that mean? So let me show you specifically. Using this. Okay. So if we cannot see this, which means like there are two possible ways to define this, the genotype of locus B, right? And also there are two possible ways to define the genotype for the locus C, right? Okay, now starting from the A is the same. So we used 1/4 here. And the transition from A to B. So in this case, we only look at the one value in the transition matrix. But because we cannot distinguish B equals to 2 or 3, so which means the transition, in this transition, we need to look at AB 1 to 2 and AB 1 to 3. Does that make sense? Yeah. Okay. And so we have to use the sum of this probability together because they are both possible, right? All right. Now from B to C, it's more complicated, right? So this involves like different ways. So either BC. So you can think about like either 2 to 2 or BC 2 to 3, right? Or BC 3 to 2 or TBC 3 to 3, something like this. So you have to consider different situations. All right. So this part is definitely required. So the simple situation. So please pay more attention on this simple calculation and make sure you understand each step. And this is more complicated. So let me think about this. Maybe I'm still debating myself. So maybe I will not put something like this complicated in the final. But at least you need to know how you use this the ideal situation. For this ideal situation, you need to know how to construct this transition matrix by yourself. And if I give you the genotype like this, so how you need to find the right element from each transition matrix to get the final answer for me. All right. Is that fair? Okay. Any questions? Okay. And okay, so for the F2 design, we also can take advantage of using the matrix notation to help us to help us code the calculation. Okay, so for F2 design, we have 4 states, right? That when A equals to 1, we can use this 4x4 matrix, and we put 1 at this element. And for the fourth, the genotype number 4, we just put 1 here. And if we cannot distinguish between the genotype number 2 and number 3, we put both 1 here and here, right? And this is the same. We use this matrix notation to do the calculation for this joint probability for the 3 loci. All right, I think, yeah, today this is a little bit like complicated. I don't want to push too fast. I'm gonna stop here. So I will use the rest of the time to help answer your question, either any questions from the previous lecture or this lecture. So anything I can help to answer you, anything I can help now. No? Okay.
I just had a quick question. This is for the chi-squared practice you gave us. Can you go over the last question in the chi-squared practice?
Do you open your file so you can share your screen and show me your question? I can stop.
Yeah, sure. Let me just pull up.
Okay. Sure, don't worry.
A lot of tabs open. All right.
Yeah.
I'll just share. Yeah, let me just pull out Windows first. It's not recognizing.
It's not working. I can try open my file. So let me see if I can find it. Okay. So you mean the last one, right?
Yeah, last one.
Oh, okay. Okay, so this one, right? Okay. Question, how, so actually this one is related to this one. So how to use R to calculate the p-value when your likelihood ratio statistic equals to this with the degree of freedom equals to 1, right? So this is the answer. Okay. So let me copy this and put this into the R. Sharing. Let's see if I can share this one. Okay, that's the probability. Okay, and how to how to understand this, right? Let me see. What's the question? So know how to explain this using the area and the curve. Okay. All right. Can you see my screen?
Yeah, we can see it.
Okay. So this is the chi-square, right? Something like this. And we know, so this is 0, and this is infinity, or something like that. So we know, like, if degree of freedom equals to 1, and the critical value, I believe, is something like 3.84, right? 84. So which means like here. So this is 3.84. So why this is the critical value? Because this value actually, so for this specific chi-square distribution, degree of freedom equals to 1, the area under the curve on the right-hand side of this critical value, so this area equals to what? 0.05, right? Which means like anything smaller than this. So for example, if you got a test statistic is smaller than it, then what do you do? The p-value will be greater than 0.05, right? Because when you calculate the p-value for this statistic, you have to calculate the area under the curve on the right-hand side, and this area will be greater than this area. Do you agree?
Yeah, I can see that.
Okay, so that's the p-value, right? So I hope by doing this, exercise, you understand what the p-value means in this chi-square test. So if you in your specific test, you got a statistic which is which is smaller than this cutoff, the 3.84, then definitely you're gonna get a p-value. P-value is defined like this area under the curve on the right-hand side of this value. This will be definitely greater than 0.05, which means you got a big p-value. You're gonna accept the null hypothesis, right? However, let's look at this example here. So this example shows you the test, the statistic is equal to 10.68, which will be some value like here, right? And if you want to calculate the p-value for this guy, you have to do the same thing. You have to calculate the area under the curve on the right-hand side. So can you tell me if this area is greater than 0.05 or less than 0.05?
It's less than 0.05.
Yes. So actually, this value is like this, right? And okay, so in this case, you see a big statistic, test statistic that is associated with a small p-value, and this will help you reject the null hypothesis, right?
Yeah, absolutely.
Yeah, okay. So this is the whole point. So I just give you this exercise so you can have some idea. So how when you get some test statistic, so what p-value you expect to see, right, from this calculation. Yeah. All right.
All right, thank you.
Sure. So I'm gonna stop here today. So I'm gonna use the rest of the time for answering any of your questions. So Adria, you asked for the office hours, right? If you don't mind, we can use this time as a office hours, or if you prefer like in the afternoon, so we can have another one. Yeah.
I'm actually good for right now. Thank you.
Sure.
Thank you.
No problem.
Because you answered the question I was going to ask about the homework. So it's perfect.
Could you say that again? I'm sorry.
I was going to ask about that question on the homework, so it's perfect.
Oh, homework. Okay. Yes. So tomorrow, I'm going to give you some other homework. For example, like the resampling, like the bootstrap. So I'm going to write some code for you. You just run through those code and get some idea. Just like today. So if you have some questions about running those code, let me know. We can discuss. And I also will give you some exercise about the matrix calculation. I'm going to write the code to help you to calculate the probability, join the probability of A, B, and C given some specific genotypes. And so when you run the code and have some problem, yeah, bring those questions to me, yeah, in the class. All right. So today's stuff is a little bit like tough, like so that's why. So I don't want to yeah, push too hard. So just give yourself some time to digest. Just review the stuff and make sure you understand those. For the final exam, so it's very likely for me to put something like that. Like I will put the easy question, like not the one where you cannot distinguish like the genotype of number 2 and number 3. So we will assume like you can distinguish all possible genotypes, 4 types. And given that, you need to know how to construct the 4x4 transition matrix and find the right element to plug in your equation to get the right answer for the observed genotype. All right, I'm going to stop here.
Thank you.
Sure.
Thank you.
Thank you. See you next week.